You and I, we use computers every single day. But have you ever really stopped to wonder how the super fast brain inside, the CPU, actually talks to everything else? I'm talking about your keyboard, your mouse, your network connection, your hard drive, everything. It's one of the most fundamental things happening under the hood, and today we're going to pull back the curtain and see exactly how it works.
I mean, really think about it for a second. Your computer's processor can do billions of things in the time it takes you to blink. Meanwhile, you're just moving your mouse across a desk. That is an insane speed difference. So how on earth does your computer bridge that gap without just grinding to a complete halt every time you do anything? That's the big question we're tackling today.
So here's the game plan. We're going to start by laying out the computer's big communication problem. Then we'll meet the real hero of the story, the I/O module. After that, we'll walk through 3 different methods it uses to manage everything, from the kind of clunky to the super slick. And finally, we'll tie it all together to show you why this matters for your day-to-day experience.
All right, so let's set the stage. The central problem, the real conflict here, is that you've got this lightning-fast brain, the CPU, trying to have a conversation with a whole world of devices that are, comparatively slow. It's a recipe for a total system bottleneck.
Okay, to really get this, let's think of it like an office. Your CPU is the high-powered CEO, thinking a billion thoughts a second. But the outside world, keyboards, printers, networks, they all work at a snail's pace. Now, if that CEO has to personally stop everything they're doing to wait for a slow memo to come in from the mailroom, the entire company would just grind to a halt. Nothing would get done.
So what's the solution? Well, you don't have the CEO answer every single phone call, right? No way. You hire a super efficient personal assistant. And in the world of computing, that personal assistant is a specialized piece of hardware called an I/O module.
And this image right here shows you exactly where that assistant sits. The I/O module is the critical bridge. It connects the super fast internal highway, the system bus where the CPU and memory talk, to all those slower external devices. It's the perfect middleman, managing all the comings and goings so the CEO can stay focused on the big picture.
So what does this personal assistant actually do? Well, its job description is pretty packed. It handles all the control and timing, making sure data traffic doesn't crash. It relays all the messages between the CPU and the outside world. It also provides data buffering. Think of it as a little waiting room where data can get organized before it bothers the CEO. And get this, it even does error detection, catching typos in the data before they cause a real problem. It's a busy job.
Okay, so we've got our assistant in place. Now let's look at the first way it can work. And, well, let's just say this is the old way. It's called programmed I/O, and frankly, it's a terrible use of everyone's time.
With programmed I/O, the CEO is an absolute micromanager. The CPU tells the I/O module it needs something, and then it just sits there, tapping its foot, constantly asking, is it ready yet? How about now? Are you ready now? The CPU is 100% tied up, just waiting on a slow device.
This flowchart just lays it all out, doesn't it? See this loop right here, where it says check status and then asks, ready? If the answer is no, it just goes right back to the top to ask again and again and again. The CPU, the most powerful part of your computer, is literally stuck in what we call a busy waiting cycle, doing nothing productive at all.
So yeah, the downsides here are massive. You're wasting an incredible amount of precious CPU time. The performance of your entire computer is basically being held hostage by the slowest thing it's talking to. Sure, it's simple to set up, but it's wildly inefficient. There has to be a better way.
And you know what? Of course, there is. Let's move on to the next evolution in the story, a much, much smarter approach, interrupt-driven I/O. This is basically the don't call us, we'll call you model of management. The CEO hands off a report to the PA and says, look, you handle this. Just come tap me on the shoulder when it's done. Suddenly, the CEO is free. They can go work on other, more important things. Then, when the device is finally ready, the I/O module sends a little signal, an interrupt, to get the CPU's attention.
And again, the flowchart tells the story. You see that little path there that says do something else? That, right there, is the magic. That's the game changer. After giving the order, the CPU is no longer trapped in that useless loop. It's free to be productive until it gets that tap on the shoulder.
So this is a huge leap forward. No more busy waiting. The CPU can actually multitask, which is what it's built for. But, and there's always a but, right? The CPU is still a little too involved. When that interrupt comes, the CEO has to stop what they're doing and personally move the data piece by piece. It's better, for sure, but it's still a distraction.
So what if you have a really, really big job, like moving a huge file? For that, we need the final evolution,
the most efficient method of them all, direct memory access, or DMA for short.
DMA is the ultimate form of delegation. This is where the CEO doesn't just hand over a memo. They point to a whole pallet of boxes and say to their top assistant, get this entire shipment from the loading dock to the archives. Talk to the warehouse guys directly. Just send me one single message when the entire job is done.
And just look at how simple this process is from the CPU's point of view. It's beautiful, right? It sends out one command to move an entire block of data, and that's it. It's done. It goes off and does a million other things and only gets bothered once, at the very, very end when everything is finished.
The power here is just incredible. The CPU is almost completely out of the picture. Data moves directly from the device to memory, no CPU middleman required. This is by far the most efficient way to move large chunks of data, which is exactly what things like your hard drive, your graphics card, and your network need to do to be super fast. Okay, this is the money shot right here. Look at these two side by side. On the left, you've got chaos, that frantic, inefficient micromanagement loop. On the right, you have pure, elegant delegation. This visualizes the entire evolution we've been talking about, from nagging to true empowerment. This is what makes modern computing so fast.
Okay, we've thrown a lot of technical stuff at you. Programmed I/O, interrupts, DMA. But what does this actually mean for you sitting at your desk using your computer?
Honestly, it means everything. The reason you can have a 4K movie streaming, a massive game downloading in the background, and you're still scrolling through a website without a single stutter, it's all because of this. Your mouse is using quick little interrupts, while that game download is using DMA to shovel huge amounts of data around without bothering the CPU. It's not magic. It's just really, really smart management.
And this right here, this quote, it really sums up the whole thing. A computer's real-world speed isn't just about how many gigahertz the processor has. A fast processor that's just sitting around waiting is actually a slow computer. True speed is all about how well it can juggle that constant storm of information from the outside world. This whole system, this beautiful dance of delegation, has been the backbone of modern computing for a long time. But, you know, technology never stands still. We're looking at VR headsets that need insane amounts of data, cloud access that feels instant, AI that's constantly learning. The demands are just getting crazier. So it really makes you wonder, what comes next? What's the next great leap beyond DMA?